Yes, so I'm going to continue studying the Chapter-4. We did this CRE, right? Did we finish this CRE 4.5 yet? Not yet? Okay, I think we finished this one.
Yeah.
Okay. So this section right now we are studying the molarities. So this is one very common unit of concentration. So let's continue on this study the molarities. As I said, molarity is a concept is very similar as density. Similar as density, but density obviously has its definition. Just remind you, so if you like still remember, density equals mass divided by volume. And usually when you calculate the density, you can use any unit for mass, any unit for the volume. Now as a comparison, so we have the so-called concentration unit, molarity, and we usually use the capital letter M to stand for molarity, and there is another word called the molar. So this view like a different way to see this same concentration, and this same concentration, molarity equals moles of some solute divided by liter of that solute in the solution. So because of this definition, it's kind of narrow those units. There you can any unit for mass, gram, kilogram, volume can be liter, milliliters. But here, to make sure when you do the calculation for these molarities, you only use moles and liters. When you do the calculation, that means if I give you some information, you want to find out what is the molarity capital M. So make sure you convert, if you have to convert the information you have for the solute into moles, the volume into liters of the solution. But when you do the calculation, use the molarity capital M. Sometimes you don't have really to use liters, the volume. So as pretty soon you will see, for example, those dilution process. You take some of those concentrated solution and you make those concentrated solution less concentrated. So in those calculations, you don't have to use liters. But at the beginning, this is the so-called definition. And so when we talk about definition, that means it's precise. So you just know like there's a definition like this. All right. I want to compare these two different quantities also because we learned some of those techniques about solving those density problems. Therefore, if there are some similarities, I want to identify those similarities. So therefore, we can use what we learned before and solve the problem like this. All right. So what we learned like before in Chapter 1, and we can use density, if density is given, as a converting fraction. So this is the problem. In this problem, you are given this molarity capital M. Okay? So very similar as if I give you density, you can use this as a converting fraction. Okay? So whenever you have this number, you can rewrite it as a fraction. So you will rewrite this as 0.125 mole NaOH over 1 liter NaOH solution. So this SOLN abbreviates as solution. Right. So once you have this fraction, and as I said in this class, the first 4 chapters, there's a lot of problems use fractions. You can use this fraction as written, or you can flip it, depending on what other information given to you. So now let's see what other information we have. We write here, so we have the other information is 0.255 mole NaOH. So you write the other information here side by side. The molarity information you rewrite as a fraction, and usually those problems you just take those two information, multiply. Maybe that fraction you cannot use right away, you have to flip it, and you will solve the problem. So you just try. If I give you these two information, and again you rewrite that molarity as a fraction, and you write the other information here as the first number, and then you can visualize, and you can see if I just simply lower down this fraction as written, and then this mole NaOH, both of them on the top. So therefore they cannot cancel out. What you do, you know you can flip a fraction. So that fraction you get right now come from that number. Okay? So any fraction you can use it one way or the other way. Right? So therefore you're going to rewrite this, you just reuse it, you already rewrite that capital M as this fraction. And so therefore you identify, you cannot simply lower that down, and you have to flip it and put it into the multiplication like this. And then whenever you use converting fraction to solve the problem, not take too long. It's very easy, just see if you can cancel out. So if you can cancel out those given units, and let's see, then you can see what unit you have left over. If the left over unit makes sense, is the unit for the quantity you want, then you pretty much get the right, do the right thing. Right. So this question asks you how many liters of this solution has this amount of mole. You cancel out more and more, you get liter of this solution. So therefore, we know we use the right fraction. Right. So then you just take 0.255 and divide by that, and I think more just 2 divided by 0.125. Oh, more than that. So 2.04 liter NaOH solution. That's really not new, because we already learned in chapter 1, and we can use density as a converting fraction. Remember in chapter 1, if I give you mass, very similar as here mass, and if you know the density, then you can find out the volume. And now here is similar. So instead of mass, gram or kilogram, you have mole. Right. So this is the example. Right. So let's do a practice. You pretty much use the same information, but there are 2 extra steps. Two extra steps. Let's see if you can recognize what are the 2 extra steps. 2 more steps than the example. is our first extra step. Yeah. So the example, you have the more. Okay? Now in this problem, you don't have the more, you have the gram. You see, that's what I tell you many times. The conversion between gram and more is so important. Okay? So you first convert the gram into moles. And then don't forget, in the example, I rewrite that capital M information into a fraction. Now you do the same, then you see you rewrite it as a fraction. You rewrite that as a fraction. That will 0.155. Yeah, you can either do that way or do that way. Very good, very good. So then you first, one extra step, you get the more from the gram. Then you have to change that liters into milliliters. That's the two extra steps. Right? Do that first. Do like converting the gram into mole. You know how to convert the gram into mole? Do whatever you can do. Right? Just take the gram. Let's do like what we can do. First converting the gram into moles. What do you use to convert gram into mole? Mole mass of KCl. Right? So do what we can do. So beginning, if you don't know like this example, you just begin by write the grams and then use molar mass convert into moles. You know how to convert from gram to mole? Okay. Do you do the conversion from gram to mole? So do the conversion first. Yeah. So that's what I want to say. That's what the mole of KCl. Right? Okay, now use what we learned today. So then, after you get the more, rewrite that 0.155 capital M as a fraction. Okay? So let's start on that and see if you can rewrite that as a fraction. You use this way. Yeah. So that's let me see. This is what? Okay, 0.155 is the capital M, and then that is the more you get from that gram, right? Okay. You can do like you can do this way. That means you solve this including get the liters, right? Yeah. And what are those numbers? Those numbers. Yeah. So once you get this liter, okay, for this problem, for this CRE, you can use this equation solving for the L. Once you get the L, you can convert the L into the ML. Do you get the mole yet? Get the mole yet? How do you get the mole? 295 grams. Then that's the molar mass of this. This is mole. So this is mole, right? Okay. Now you just write down this is 0.039 mole of PCl. Okay. Then you rewrite this capital M as a fraction. That means you have 0.155 mole of PCl. Write somewhere else. Write that somewhere. Then you decide whether you can use that or fit that. That's right there first. If you recognize your freeway, right? Very good, very good, very good. Sure, this number. Yep. Now you can see you can write them together more PCl. Therefore, PCl. That's see, this is what we learned before. Right? This is the fraction we learned divided by this number, right?
Don't ask me why.
Before I got here, so.
So then this is theta. This is theta. And you multiply by 1,000. Alright. So what's the answer? Anyone need some help? Huh? What do you get? Okay. A? Okay. Let's do it together, okay? Let's summarize these few steps, okay? If I put everything together, so I tell you to do what first, but after you get familiar with, you can just put all everything together. So I will start with 2.95 gram PCl and multiply by the converting fraction from the smaller mass. Right? Someone tell me exactly what is the molar mass of KCl. I saw like someone you do 74, right? 74 what? 0.55? Okay. Okay, so let me make a note. This is from what? From molar mass. Okay? That's, if you forget, make sure you review this. This is a very important step. Right? And you can see the calculation is right. So the gram KCl comes out. So this is one of those extra steps I tell you more than the example. In the last slide, in the example, you don't have this step because in the example you are given how much more of the solute already directly. Now this program you don't have the more of KCl, you have the gram of KCl, so you add in this one extra step. Okay? Now the second step, it will come from this guy. Okay? Remember when I tell you to do this one first, or to do this one first, to do this conversion first, then rewrite that as a fraction. Okay? So now let's rewrite that as a fraction. And if I write on the top, I will get 0.155 more KCl over 1 liter KCl solution. Now this fraction is very similar as a very straightforward rewrite. No flip, and just instead of like writing this capital N, you just write this more over liter. You're adding a few informations, per means 1, okay? And those KCl because it's referring to the KCl. Okay? So make sure you understand those similarities. So if I give you 0.155 capital M something, you can write that 0.155 something over 1 liter of solution. Okay? Whether you can use this fraction right away or flip it, you can. Okay? So in the examples, we have to flip this one, 0.155 more. I will write that at the bottom. Okay? So this together like this, then you have 1 liter PCl. So I will write on the top a solution like that. Okay? So if I write this in this way, which means I did not use that fraction as what I get by simply rewrite those numbers. I flip it. So 0.155 there is on the top, and here I put at the bottom. Okay? That's because we know if I do this way, this more KCl cancel out because 1 on the top, 1 at the bottom. Right? So this step, you saw it in the example. Okay? So this is our extra step. Okay? Than our example. Okay? Now there's another extra step than the example because all those answers here is ml. Okay? Now what you have right now is L. Okay? So you are adding another fraction, and then you put this fraction you are far away, and put it here. Okay? So you know like 1L is 1000 ml. You can keep those, also keep those informations, 1 L of what? What we know, 1 L of PCl solution. Then if you add in this PCl solution here for the L, you will also do the same for the ml. Right? So here we also PCl and also the solution. Right? So then the concentration also similar. So here the cancel out, and here cancel out. Cancel out everything. You have to say L cancel out. L what? L KCl. KCl what? KCl gas. KCl solution. So sometimes you omit, but you know that you omit in your mind. You know that. So obviously these few number multiply and divide, you get the answer A.
And why did you multiply by 1000?
Because before you multiply by the 1000, before this one, you have the L, which is the liter. And here is the milliliter. Okay, any other questions? Yeah, that's why I want to say you should very quickly, know that depends on your how much you study. You might be very busy in the daytime. If you have some question, don't hesitate. Just ask the question right away. Right. Similar problem. Remember what we did in chapter 1 for the density problems? Okay? So now, again, I give you this information, this guy. So what I suggest is you can write this 1.05 L, this solution first, this volume first. Then think about how can you use the other information and cancel out the L. If you do that, so this is one information you have in this given problem. So we run that first. Then how can you use that other information cancel out the L? Let's start from that. Once you cancel out the L, you see what you get. Then you will see how can you get from that intermediate to the final answer. Right? So you write 1.05 liter of that solution, and then how can you use the other information cancel out that 1.05 liters? So in this way you have that this fraction come from what? Molarity. And then you can use it right away using a fluid, right? And this fraction, another fraction comes from what?
That's in the raw mass.
Yep. You want to write out on the board and see like what? Yeah, you read what I write there in the middle. Right? So let's keep working on that. What do we get? So what do you write? You write that write what I said like 1.05 liter first, right? Then what you do to use other information is that molarity, right? You rewrite molarity as a fraction. Okay, so some of you like to use the other way. You can just have those information and summarize and put in that equation. Just just erase it. That is the definition of molarity.
Is it B?
The answer is B. I did not remember. I did not check. So probably. So we'll see like what he writes the steps, and we will see the numbers. so answer is B, right? Okay, Brad, you can explain like step by step, and what do you use? Okay, why you use in that way?
I started with the liters of sugar, and then I used molarity in this conversion fraction because it gives you the moles of sucrose, and you want it over 1 liter, so that cancels out with this here. And then in the next part, you can just use the molar mass to cancel out the moles here. And after multiplying and divided, we got the
Where you get that, did you see where you get that second fraction? Molar mass, right?
yeah.
Any questions? Any questions? Good, so if, that I said, if Brad like you read this line, right? So you cancel out this with this, that's what I was talking about initially. You get this information here, right? So that's like you use like the information give you like a derivative. Just take the liters multiply by this molarities, you get moles. Then you see you get more. Well, that's not really exactly what's those answers. Then you know, like what I tell you many times, the mole gram conversion is so important. It's become like a very similar. So that means if you know the moles, you can get the gram right away. All right. So that is few problems of use of molarity as converting fractions. Okay? So make sure you know if I give you the capital M, you can rewrite, and you know that you can use it or free it. I know a lot of you like to use the other way, but if you can solve the problem very quickly, use the other way, that's okay. Okay? The other way is capital M equals mole over liters. So therefore, you can just put whatever the molarity give to you, and put whatever the other information give to you. For this example, you have this number, you have this number, you put into this equation. You don't know this number, you can solve this equation very quickly to get this number. Then again, you recognize, well, I need more for. I need those the other number, I need the grams, but you can know like once you get the more, you can get the gram very quick. All right. So now let's move on to like another section, which is about dilutions. Very important technique in the chemistry. Okay? So especially in the lab, and in the lab you usually prepare the solution concentrated. Okay? So when you use a solution, you don't use those concentrated solutions, and you even see those concepts in your daily life. You like make some of those coffee or tea or sugar waters. So if you put too much sugar in your sugar water, you feel like it's too sweet. What do? You have like 1 cup of sugar water. It's too sweet. You just pour the liver out and then put a lot of water in. Then your sugar water becomes not that sweet. Similar, so you have those chemical solutions, and this picture tells you this little darker blue, which means concentrated. So you can take a little bit out from this solution, and you have to know how much you take out because you want to do the calculations. Usually you take out like by use those pipette. So you pipette some of this out, and you put in the other flask. So then that is how much you take out. You call that like maybe V1 or V2, so whatever you call that. So then you will know like one number called V1, and then that concentration will give to you, if you call that this in the pipette is V1, then the concentration of this darker blue will be M1. So then you just learn in those techniques, right? So in this example, if you know this how much liter you take out, and you know like the molarity, you multiply and you know how much more of those solutes in this solution you take out. So once you take that out, you put in this other flask, and then this is why we say, once you do the dilutions, you take those solutions out, then your more will not change anymore. So what it will change is only the volume. Okay? See here, the amount of solute does not change. Just the volume of the solution, what that means is if you want to dilute this dark blue solution, you use the pipette, take one full pipette of this dark solution out and put it in there. And that you can calculate, or you will know how much more of that dark blue solution you take out. And that amount of more solution in this flask, in the second flask, will not change anymore once you take that out, if you don't add any more. Okay? So once you take that out from this flask into that flask, you know how much you take out. What you adding now, you are adding solvents. And usually the solvent in the general chemical class is water. Okay? So that's what we mean by that. Right? So based on that statement, and we have this equation. Okay? So once you take the solution out and put it there, and you keep adding water, then you have that amount of solution now. And this amount of solution, the volume becomes V2. The concentration becomes M2. Because after you take that much solid out, the other only thing you add is water. So therefore, when you multiply the M1 V1, you get the more, like what Brad did here, and that more will not changing, even though you add water. Water don't have those solutes. So therefore, in this solution, in this new solution, and you take we have that V2 and we have that M2, even though M2 you probably don't know, but you know that M times V will be the more, so more for equal, so therefore you have this equation. So in this calculation, it's a little like a straight. I mean, it's not that flexible. Now in this equation, it's a little more flexible because the volume here, so these two can be in like any unit of volume. Can be any unit of volume. You don't have to change that into liters. Even though this guy still has that more over liter. Understand? So even though they still have more over liters, but when you do the calculation, use this equation, you don't have to convert V1 or V2 into L. You can keep whatever that unit that has, as long as you know you will get the same unit. If you use unit as the liter for this one, you should get the liter for the other one. If you use milliliter for that one, you will also get a milliliter for this. You can even use ounces or whatever those units. Why? Why you can use any units?
The units have to be similar to one another.
As long as they're the same. Why you can use like different units? Let's see this M1, some of those numbers. And let's see if you use liters, use milliliters, right? If you use milliliters, it will be different than this format. In this, what Brad did here is use liters, because liter and that liter will cancel out. When you have this M1, M2, you know in the denominator you have liter. Okay? But if you take L, you cannot cancel out that L in this M1. Do we have an L in the M1? Yes. Okay? M1 is another name for the capital M. Right? Remember that capital M is our molarity. So molarity will always have that liter in it, and sometimes we call that M1, but it's still capital M. Right? You probably want to use some numbers. Let me just give you this number here. Okay? I use number easy to say. Okay? So let's see, I have this molarity here. We call this will be our M1. Okay? This will be 0.758 more. Something I call that A. Okay? And over 1 liter of A solutions. Okay? Now, as I said, if you want to use this equation to do the calculations, you don't have to convert this volume into liters. Let's say we use this number we use like 25 ml. And 25 ml. Okay? Right. So I will multiply 25 ml here. And so then I will say from this equation, so this will be our M1. So this is same as our M1. And this will be our V1. Alright, so now our M2, usually we don't know according to this picture, okay? And let's say our V2. Okay? And our V2, let's say this picture will tell you this flask is about volume 250 ml. Okay? So I will put here 250 ml here. And then this capital M, M2 I don't know, so I will call that X more A over 1 liter of A. Right. So you don't have to convert this ml into L like what Brad did here. Okay? The reason is, if you do the conversions, how you do conversion from ml to L? Okay, let's see, 25 ml, how you convert into L? What would be the fraction looks like?
Divided by 1,000.
Yeah, so 1,000 ml and 1 L. Okay? So if you convert, you just use this fraction. Okay? Now let's add in this fraction here. So if I put this fraction here, 1 over 1,000 here. Okay? If you do that, you also do that for this volume. Right? So therefore, you also have 1 over 1,000 here. Okay? Now this is the equation. If you have 1 over 1,000 on the left side, you have 1 over 1,000 on the right side, what happens? What will happen if you have this 1 over 1,000 on both sides of this equal sign? What will happen? That will come out. Okay? So this comes out, this comes out. So that's the reason when you have an equation like this, you can use any unit for the volume as long as they are the same volume. And similar for the capital M, M1, M2. Right. So make sure you know like this concept. Right, so now let's do some practice. The equation you're going to use is M1 times V1 equals M2 times V2. So just do the question carefully. Sometimes it will difficult to recognize which one pair up with which one. Right, so by reading the question, we can see I will call this V1 and this will be our M1, and then this was our M2. So even though both of these concentrations is 15 M, simply called M, and there's a 3M, simply called 3M, so I said, and because you have a 2M, you want to tell the difference, you call them one is M1, the other one is M2. But the definition is still similar as what we write here. Right. So once you identify like this, you are you will just substitute those information into this equation. So we will have 15.0 capital M here, and then we'll have 0.200 L here. And so then you have equals 3.00 capital M here, then V2 here. Right? So that's what a very simple algebra equation. And you can see this capital M comes out. So in this comes out, is a little different than the comes out what we write here. And this comes out, we don't have an equal sign. They're on the same side. Therefore, you have to put minus 1 on the top, 1 at the bottom. Now in this calculation, it's in an equation. In an equation, you come out, that means these are at the same place. It becomes a very simple problem, so therefore you divide by 3, and divide by 3, and you get 3 comes out, become 1, then become 5, and you get 1.00 L equals V2. Right? Yeah, so that's the problem. Alright, so do a very similar calculation. Identify what is your V1, what is your V2. So this, well, let's check and see if you understand what I said here. You don't have to convert the volume into liters. Well, you already get some answer? C? Okay, how you gonna see? Do you assign those M1, V1? What is your V1? What you're looking for, okay? You want to prepare this much of 250 ml, and so these two will be together, right?
Yeah, that's
250 will be V2, then this 1.25 will be our M2. Excellent, excellent. And then that other concentration will be our M1. And then V1 you don't know, right? Okay. Very good. So therefore you don't have to convert the ml into L. Even though it looks like it doesn't make sense because ml times capital M will not really give you the more because the ml cannot come out. But actually before you multiply this ml into that unit, this capital M comes out. Yeah. So that's another way to understand, and you don't have to convert the L into ml or ml into F. Right, so what's the answer?
C.
Okay, good. So I think this type of problem probably we can understand a little bit easier. Okay? So what we did is we will give this, I think some of you call this will be our M2, and this will be our V2, and this will be our M1. Well, which one you call one doesn't matter. You can call that you can call this one is our V1, this will be our M1. Then you will get the same answer. Okay? Just be consistent, like which number pair, which number, right? Right. So the equation again you're going to use is M1 times V1 equals M2 times V2. If we call this our this 250 is our V2, and 1.25 is our M2. So we just substitute into those equations, and you will see this. M1 is 3.50 capital M, and then V1 equals this, and then you have 1.25 M is our V2, then 250 ml is our V2. Right. So then you can see the cancellation depending on what you like. If you want to cancel out right now, you will see that this capital M is the capital M cancel out. Okay. Alright, so therefore, and then you divide by 3.50, divide by 3.50, Then on the left side, you have weight 1. On the right side, you have 1.25. That capital M is similar, so this 250 ml comes out and keep it here. Right? So that's very straightforward. So after you do the calculation, you get the answer is 89.33. Right? Alright, any questions about this very basic, very important concept of molarity, capital M? Okay? So you know the definition in the molarity, again, I emphasize or recall in the literature, but in reality, when you do the calculation, like in the last example, to the dilution, you don't have to use liter, okay? As long as you have an equation, okay? And you keep use ml for both solutions, then you get ml, is fine. Right? So now let's see what happens when we prepare those solutions. We will have like some of those either like some of those liquid or solid or even gas materials, right? Dissolve in the solvents. Your solvent in the general chemistry usually is water. Okay? So once those solid, liquid, or gas get into water, that's our first step. Okay? Whether those get into water significantly you can notice or not, and that will call them different things. We call them soluble or insoluble. Right? So those, in chemistry, those lines are not very sharp cutting line. If I tell you, like in what we did, like in the lab, one lab, like that last week at the lab, or the week before last week at the lab, we have those precipitations. So you prepare, you see like some of those solids come out. Once you like have those solution, you put those HCl in it. You see the precipitations. That means AgCl and PbCl2 or mercury 1 like Cl is not soluble in water. When we see that, it's relatively speaking. So I said insoluble, that means like there is nothing like in the water. Okay? It's so less you cannot notice. Okay? So keep that in mind. And right. So now let's think about those dissolve is our first step. Okay? So dissolve that means that either solid or gas or liquid get into water. Okay? Everything can get into water a little bit. Okay? If you get into water too less, we call that insoluble. Okay? Now we're going to talk about those really like something can get into water a lot, so therefore we call that soluble. Okay? So let's see. Once that happens, and depending on what is your solute, and so they will have some different things will happen. If you want to understand how can those solid, liquid, or gas. Solid example is NaCl. So that we call that is kind of insoluble. So we're not going to use that as one example. But that's 2 liters dissolved in water. NaCl, the type of salt, is soluble. So what happens if you put those NaCl in waters? And how can that happen? So what happens, we'll start that later on. How that happens is depend on those forces between those something. We pretty much have 3 things we can see here. You prepare a solution. For the simple solution, like one solute, there's always only one solvent. So 3 things you think about. One is solute, and the other one is solvent, and then the other one is the solution. Right. So these 3 things you think about, you will understand whether you can, produce a solution, which means whether that solid will get into water a lot or not. Think about these three things. So before you put these solutes, for example, this NaCl into water, NaCl, like the solutes, is solids. So there are some force in there. Let's see this picture here is our NaCl. Right? So NaCl has those ions in it. Right? So there are some of those attractions between this one and this one. There's some attractions. So therefore, you will see that NaCl stuck together at a solid in room temperature. Right? Then the other one is water. The solvent is water. Right? So solvent also have those interactions. Right? So between this water molecule, that water molecule, there's also attractions. So therefore, you have those that water stuck together as a liquid. Right? Now for this NaCl separates, for this water separates, we need some force. Otherwise, this cannot squeeze in. Okay? So what happens if the attraction between like this solutes, this water, and this, so that means we need to. So if you have the force between like those initially those between the purple and purple, and between this green and green, so they're all like those attractions. And then once you put them together, there's also attraction between the purple and the green. So usually when those magnitude, when those strengths are comparable, and then your solution can be produced. Okay? Right? So that's in this picture about. Well, in general, you have to use some of those. You can do your study a little more detail. You can do use some numbers, calculate, and so for right now, we just think about get a rough idea like this. Now, so this is the very, very basic concept about the dissolve, which means you have a solid, looks like disappear in water, and that happens like that. Okay? Now let's talk about the second step. Okay? After those something disappeared, and let's see what happened to those disappeared. Okay? Well, they're pretty much like, probably not always true, but we can see that in general, there are three things that are true. So those, as we learned in Chapter 1, Chapter 2, we have those compound. Compound can be ionic, can be molecular. That will give us roughly two groups of those solutes. So if your solute is ionic and is soluble, well, even though it's insoluble, it's still a little bit will get in the water. Okay? So you can understand those insoluble in a similar way as the one for soluble. The only difference between the soluble and insoluble is how much. Okay? When we see the soluble, that means there's a lot dissolved in water. When we see the insoluble, that means a little bit. Okay? But what happens after they dissolve in waters for the ionic compound, same. Just the difference is how much. Right? There's depend on the book. So how much you think you call that something is soluble? You have this number 0.01 capital N. If your solid, like those NaCl, or maybe like many of those compounds, ion compounds soluble in water, which means you can calculate the maximum concentration before you see the precipitations is more than 0.01 capital N. If you can get a solution like that from some of those compounds, and you see that compound is soluble. So all the ionic compounds, when they dissolve in water, similar things happen, just depend on how much. Right? What happen is has this terminology called dissociate. Dissociate, which means separate. So this equals separate. Simply separate because before they get into water, you, for example, you have that NaCl, and in NaCl, we know we have Na plus ion, Cl1 negative ion. But before you put that in water, so the attraction between these two ions is so strong, the air cannot pull them out. So therefore, they start together as a type of salt. If you put that in water, they dissolve, they disappear. If you don't put too much, if you put too much, then you will see at the bottom there's some of those NaCl. So if you see that disappeared, actually, that disappear process for this particular example is called the dissociate, which means the Na ion is separated. Usually they are far away from the Cl ion, and both ions is wrapping up by some of those water molecules. Right? So this is what happened for this ionic compound. Right? The next group of compounds, remember we see the compound can be ionic or molecular. Right? Molecular compound, usually for most of the molecular compound, and for example, ethanol is a major component in the beverage, in beers, in wine, in liquors. So you have the methanol, which has the formula CH3CH2OH. So typically molecular compound, if they are not acid, not a base, and they can dissolve in water too. Even though before they dissolve, they are also liquid, but they can mix with water. Now typically, if your compound is molecular like this, if you take like 1 cup of ethanol, then you take 1 cup of water, you mix them together, you will see no difference. There's no layers. You just mingle together very, very finely, very, very like uniform. So what happened for this mixing is a little different than the mixing of NaCl with water. NaCl mixed with water, Na become Na ion, initially Na ion, but separated with Cl ion. Now this ethanol, after you mix, all those atoms still together. They will not separate, they will not become ion. They just mix with water on the molecular level. So this is one type of molecular compound. The other possibility for the molecular compound is those acid or base. A common example of acid is HCl. HCl is also a molecular compound because as we studied in chapter 2, in this compound HCl there is no metal and no ammonium ion. So there are two things we try looking for the ionic compound is not there. Therefore, this compound is molecular. Now, if you take this molecular compound, and usually that will be gas, which means you bubble some of those HCl gas in the water, the bubble disappears. Which means those HCl really get into water. So now this HCl getting in water is a little different than the ethanol getting in water. Ethanol getting in water, so ethanol is CH3CH2OH still together as a group of atoms. But if you put HCl in water, so this will separate into H plus and Cl1 negative. So they will not start together anymore. Right. So that is like a 3 type of process happens when something dissolves in waters. In the picture, you probably see that really easier. For this example is our ionic compound. Table salt is one common example of ionic compound. Okay? Ionic compound again usually has very, very smaller solubility. Okay? If the solubility becomes so small, becomes less than 0.01 capital M, we will simply forget about it. We will say that is insoluble. But that's the similar process, so you just see a very, very small amount. And then you can see this picture tell you the ion separate. So negative ion, positive ion, separate apart, and each ion wrapping by some of the water molecules. So because you have those ions freely floating or swimming in water, it's very similar as you have electron in a wire. So while we have the electricity, we have the copper wires, so the electrons, literally the electrons can move in. They move a little bit slower, probably just 1 centimeter like per minute. They move very slow, but they really, the electron can move. And so then you will have a similar movements for those ions. So ion carry those extra electrons or carry some of those deficiency of electrons. You might have extra electrons, you might have less electrons than protons, then you have a charge. So therefore, if you have ion in your solution, in water solution, so this ion can freely move in. And freely moving charged particle can conduct electricities. You can see this picture show you have the battery, and you make a circuit. You probably play those games like in the when like in some of those class, do those experiments in some of those class. You can see the light up. Right? If you want to compare in this solutions, you don't have those ions because you dissolve like sugar. So sugar is another example of a molecular compound that will not dissolve, not separate, even dissolve. So you don't separate, you don't produce ion, and therefore your solution cannot conduct electricity, then your light will not light up. So then in this chapter we're going to learn a new concept. So referring to those substances, if your substance, remember substance, substance can be like an element or compound. Usually the element will not do those. The elements usually cannot produce ions. So those compounds dissolve in water and produce a solution. If your solution can conduct electricity, then the compound that dissolves in water, you call that compound is electrolyte. And then if you have a compound that can dissolve in water, but after your compound, for example sugar or ethanol, dissolve in water, you have a solution, the solution cannot conduct electricity, and then your compound like sugar or ethanol, we call those kind of compounds non-electrolyte. So later on, for those electrolytes, we will tell their strengths. So some of those compounds, they dissolve in water, and they will produce 100%, and 100% of them change into ions. And then we call those kind of compounds strong electrolyte. If the compound get into water, we call that dissolving water. So again, if 100% of them, well, if you want to precise, that probably not true, but in this case we'll see 100% of them. So we'll see 100% of them become ions. We call those kind of compounds strong electrolyte. So this electrolyte will have two like smaller group of this. Strong, which means 100%. If you study in chemistry 101, this 100% become not that precise, but for right now we say 100%. And so then the other one, not 100%. We call those kind of compounds get into water solution, get into water, you can still conduct electricity, but your electricity light was not very bright, kind of dim, and we call those kind of compound, it's still electrolyte, but we call them weak electrolyte. Right? I think this concept is very straightforward. Right? So let's see the molecular view. Okay? What do we mean by the electrolyte and non-electrolyte? I think that probably already get that picture. So for the non-electrolyte, it pretty much there's no ions. So again, those no ions just in some sense no ions. You so less you pretty much forget about it. Okay. So even like pure water, you see pure water will not conduct electricity. Okay. But you know like pure water has about 2 times 7 times 10 to the negative 7 molar. Not 7. 2 times 1 times 10 to the negative 7 capital M. It's about like 2 times 10 to the negative 7 capital M. That amount of ion in pure water at room temperature. So they're very, very small. Right? So therefore, we usually say that there's no ion in those. Right? So if your compound get in the water will not produce new ions, and obviously your solution will become like a non-electrolyte. Right? So that's about these 2 basic concepts. I think that's we'll see enough. And let's see the difference between like that. Again, compare the table salt and sugar. You see the table salt on the left side. Table salt is ionic, and that dissolve in water and simply separate apart, become a lot of ion in the solution. And this, let's say, this is sugar compound that also soluble in water. Soluble in water also have a limit, but forget about what I'm repeating. I just want you to know those extremes. Right. So once you have the water dissolving, once you have the sugar dissolving water, so sugar will pretty much keep intact. There's no breaking apart, and there's no ion produced. So therefore, you have those kind of solutions, and your solution cannot conduct electricity at all, pretty much. Now, as we emphasized in the first slide of this section, so some of those molecular compounds are those acid or base. So even though before they get into water, there's no ion in themselves, but water can help them. With the help of water, they can produce ion. So in that process, we call them ionized. And you can see the word a little like subtle difference. Dissociate, which means you have ion at the beginning, simply separate. Ionize, which means you don't have ion at the beginning, but with the help of water, you can produce ion. For the acids, one typical ion you can produce is H+, according to one definition. So I don't want to confuse with you like about too much of those acid-based definitions. So that we will just say like we have those. Whenever we have acids, so we will have this H+ ion produced. The H+ ion might come from your compound, like in the HCl, might not. But as long as you have something that gets into water, and together with water, give you H+, and then we'll call those kind of compound as acid. Similarly, for base, I did not put in this on this slide. So if you have some compound and you put them in water, give you that OH, one negative, hydroxide, and this will be our base compound or basic compound. And Right. So depending on how much the molecular compound ionize, we call them strong or weak. Especially for the acid, acid HCl initially intermolecular, HCl and HBr, I write them a little like far away, and precisely all of them should have the state like aqueous, as what we studied in chapter 2. So Hi and aqueous and HNO3 aqueous, H2SO4 aqueous, HClO4 aqueous. So these are 6 common acids in the general chemical class. In some other chemical class there's more, but we start with these 6 very common strong acids. So that means these 6 strong acids, committing them to memory, because that's very, very useful later on for this chapter and other chapters. Which means if you put these 6 compounds in water, and they were 100% ionized, 100% ionized. So therefore, we call this 6 acids is our strong acid. Also, you can notice in this 6 acid, and only one of that has 2 H. All the other 5 has only 1 H. So this has 2 H. From the diprotic acid, di means 2, proton, which means H plus, diprotic. All the other 5 is monoprotic. Mono means 1. So all the other 5 can only give you, for each one of those molecular formula, can only give you 1 H plus. And this H2SO4 is only one example for diprotic strong acid. Now some other acids is also diprotic. The carbonic acid, the chromic acid. So a lot of acid is diprotic, but only this sulfuric acid, H2SO4, is a strong acid. In the first step, you have 2H. I think at one class we talk about you have 2H. You're going to take the H away step by step. You take the H away, the first H away, and that first step is strong, which means you have 100% of H2SO4 do not exist if you put that in water. So all those 100% of H2SO4 disappeared. So this is sort of the strong acid. So committing this into memory, because later on you're pretty much going to use many times. You can use the equation. Chemistry is about the change. So any chemical process or physical process, the chemists like to write up an equation. So you are usually start with what you're starting from, what material you're starting from. So for this ionization process, you can write HCl aqueous, produce H plus aqueous, and Cl1 negative aqueous. This is the ionization process. You see in this equation, there's only one arrow, and this one arrow only have one arrow, which means 100%. Now we compare another arrow. Another acid, HF. HF not in that list. So I think you already, like take the notes and you write that 6 acid. We call that strong acid, right? So again, use elimination. HF not in the list. Right? So for this class, if you don't see those in the list, you call it weak. If you know that acid from what we learned in chapter 2, you call that a weak acid. For the weak acid, we will see 2 arrows. Okay? Arrow pointing to the right, arrow pointing to the left. Okay? Well, this process can go from left to the right, and also can go from right to the left. And so you have a dynamic process. So finally, they become equilibrium. So therefore, you will have like a certain percentage of HF exists as HF. In your solution, you can measure it. You can measure it, you still have this HF bond there. You can use this technique and you can measure HF, still have the covalent bond there. Right? So this is about the strong acid and weak acid, and also give us a very good sense of some of those molecular compounds, even though they are molecular before they are dissolved in the water, but with the process of dissolving water, they become some of them change into ion. Maybe all of them change into ion. Right? So now you know if the ionic compound is soluble, they will totally separate 100%. If you have a strong acid solutions that are also 100% being ions. Now we will pretty much complete our definition for those strong acid, strong electrolyte, weak electrolyte. Right. So then I wanted you to memorize this definition. And this is the so-called strong electrolyte. Right? So strong electrolyte is a very important concept. And it's so important, and I'm going to write it here on the board, and later on I'm going to use it. Strong electrolyte has these two smaller groupers. One smaller grouper is the strong acid, and the other smaller grouper is the soluble ionic compound. Now for this class, the strong acid only has like six examples that are easy to memorize. So there are 6 strong acid: HCl, aqueous, HBr, aqueous, HI, aqueous, NO3, aqueous, and I have that HClO4, aqueous, H2SO4. Right. So these were our make the line here. So these were that 6 strong acids. So whenever you see these 6 strong acids, you call them strong acid, and they also belong to this group of compound. We call them a strong electrolyte. Right. So the other smaller group of strong electrolyte, but by the way, strong electrolyte sometimes I will simply call that SE. SE means strong electrolyte. The other smaller group has 2 key words in it. One is soluble, the other one is ionic. Because we have these 2 key words in it, so therefore, to be a strong electrolyte, you have to see both of these words are met. If the compound only like satisfy one of these words, then your compound obviously is not the strong electrolyte. Okay? Understand? Right. So very, very important in this chapter. Okay. The reason is if you know they are this Se, the strong electrolyte, that will tell you immediately if you see those guys followed by the AQ, which means they like in water solutions, then in your mind you know they are no longer exist as those written. Even though as written is what you prepare in the lab. Okay? See, in reality, when you put them in water, your notation like this, but you will understand those will exist as 8 plus and the corresponding negative ion. Okay? And similar for this type. Okay? For example, one of this is you will see like many times NaCl, like aqueous, and let's see something else, NH4, NO3, aqueous, sodium chloride, ammonium nitrate, and those are soluble, so pretty soon you will see that solubility rule, and they also satisfy the other word, because both of them is ionic, and therefore you know these two also belong to this group of so-called Se. So what do we mean by those Se? Is in those water solutions, 100% as ions, and that is very important in this chapter. So now besides this strong electrolyte, there's another smaller type of electrolyte. We call them weak electrolyte. So no matter they are strong electrolyte or weak electrolyte, if they have that word electrolyte in their name, which means if you put those compounds in water, more or less, they will give you some ion or produce some ion. So for the weak one, for the weak electrolyte, which means they will not 100% become ion. But they will still give you some ion. Another point about this become ion process is again another point about those compounds become ion. That process is if the compound like this one, and we finish this process, if you see this NH4 NO3, this ammonium nitrate AQ, so as we said, because this is a soluble ionic compound, which means you will see this 100% become ions. Now ion, you have to see like what ion do you have. So in this example, we have the so-called polyatomic ion. Polyatomic ion, when you have this separation process, so this NH4, so this is one polyatomic because you can see there are 5 atoms together. So you don't separate like this N and H separate apart. You only separate this NH4. So that's one ion, and then the other one, the nitrate, is very similar. So that will start together as the negative ion. Okay, so that is one point I want to mention about this 100%, or even some of those weak electrolytes, not 100%. Okay? So in general, it's about this process of become ion. Okay? The process of become ion, you don't have to like really separate everything. For that example on the top, you don't have those polyatomic ion. So therefore that Na just simply become Na plus ion followed by the aqueous. And then the Cl is very similar. So Cl just itself become like that Cl negative aqueous. Okay? So this is the two process for the strong electrolyte. Right? Okay, this last element. Okay? So when you have those ion called the polyatomic, okay? So for the polyatomic ion, you keep them together, stay together in this process of become ion. Right? Even though for those weak electrolytes, because here I have this is for the strong electrolyte, so therefore I don't use that example. So in the example for the weak electrolyte, and for example the acetic acid, which is the component of acid, the salad dressing or vinegars. So there's a lot of H in this formula, but only the first H there is sort of the negative H, and that H has the possibility to become ion. Because that is weak, that means not 100% of that, even that first H, not 100% become H plus. Okay? For this acetic acid, if you do a calculation in Chem 102, much less than like 1%. Much less than 100%, obviously. Even less than 1%. Okay? So therefore, in this statement, I'll show you, you have the H plus, but the negative ion, again, the polyatomic. So you have everything together, either this as like one ion. Okay, any questions? Right. See, I think I even started enough now, right? So recall, we have this, making a solution process, we have two steps. Dissolve is our first step, right? So dissolve is before this. Before this, it's called the dissolve, right? Dissolve is you take something, take the solid, liquid or gas, and get into the solvent. So that's simply referring to that process. Okay? You can take a sugar, put it in water, that's dissolve. You can put a table salt in water, that's called dissolve. You can put ethanol in water, that's called dissolve. Okay? Now after dissolve, the second step, so on this side, this is what happens, might happen. Okay? And if something not happens, that's simply called the intact. Okay? And right, so two possible something can happen is dissociation for those ionic compounds. And here again you see the example and another example for sodium sulfide. So this two process, right? So these two examples, the first two examples is about dissociate. What do we mean by dissociate? Is your compound initially has ion in it. You put them in water, the ion separates, really become ions. Now this called ionization. Ionize, which means at the beginning in the formula, in the molecular formula, there's no ion. Okay? There's no ion because you have a covalent bond. You don't have ionic bond here. Right. So then with like the help of water, so that become ions. Right. One point I want to mention. Okay? In this process of emphasize, is dissociate, ionize, and I want you to recognize or read those equations. You can see the equation here. Okay? Initially, you have those compound formula, and then here you don't have the compound formula. You simply have those ions separated. That is also very important. Okay? They kind of like doing what we did in Chapter 2 to the reverse. Right? Remember in Chapter 2, you have this ion switch, simplify, get the formula like that. In this chapter, you want to do the reverse. So if I give you some formula like that, and you should be able to identify what ion should exist and how many it should be. Right, so in this first example, we know we have Na ion, Na plus ion, and then we have that sulfur ion, something from sulfur. Right? So what we studied in chapter 2, so something from sulfur by itself, or we S2 negative. You have only one S2 negative, and you have two Na1 plus, and these two come from that two. Right? So these two come from that. Alright. So the second example is the sodium sulfate is also ionic. Right? Ionic compound. Yeah. What's the question?
Two negative on sulfur.
Yeah, remember you use this sulfur, like you can predict it, this group of 6A,
6 no.
that's 6 minus 8.
I have a question. So, with like sugar, that wouldn't dissociate or ionize then?
Sugar, no, you mean the usual sugar, the table sugar, right? Sucrose, no, they not too much, probably like only like 10 to negative 9, so just
Okay.
forget about that.
Alright.
Right. So then if we can ionize like those acid or base, to something you can notice, then you know you will have those ion in the solution. So usually for most of those molecular compounds, you put them in water, they pretty much keep it intact and keep everything together. So you don't see like any breaking apart or become ions. Right? So as I said, it's kind of like the opposite of what we learned in chapter 3. And here again, these two come from this. Okay? And this SO4 together pretty much not like separate, but you still want to see this SO4. There you don't see any charge, even though in your mind you know SO4 sulfate is 2 negative, and here you can clearly write out SO4 2 negative. So depending on the problem, you can in the lab you want to prepare like sodium sulfate solution, and obviously you go to the lab, so you will see you have to see like the sodium sulfate or the sodium sulfide in the bottle as a solid, and then the bottle label will tell you is Na2S or Na2SO4. So therefore you're starting with that, but in your mind you know like if you put those in water, they do not exist together as a solid anymore, they will separate. Right. Now this table summarize, I write like only the strong electrolyte out, okay? But in general, you will have some other weak electrolyte. And also the last one, non-electrolyte. So these are 3 common group of compounds. But depending on what you do, you can classify compound into many different groups. Okay? So make sure you can follow the direction of this table. Okay? If I give you a compound, you can identify is your compound a strong electrolyte, weak electrolyte, or non-electrolyte. Right? Right. So let's start from this group right here. Okay? What is strong electrolyte? See here, strong electrolyte is soluble, ionic. Then for those molecular are those strong acids. So it's similar to what I write here. So different way of organizing our knowledge. Okay? Learning has like 7 different layers. So the first few layers is memorize and organize your knowledge. Then as you do more, you have to learn how to use your knowledge. Okay? So it becomes more and more complicated. Right. So the first group is the strong electrolyte, which means soluble ionic and strong acid. So that's our first group of compound. Okay? And now let's see what is our second group of compound. What is our weak electrolyte? What is our weak electrolyte according to the table? Anyone can read this table? Huh? What is our weak electrolyte?
Weak acid and weak basic.
Yeah, only these two possibilities in this class. Yeah. So if your compound, okay, in these two groupers, these two smaller groupers, you know your compound is a strong electrolyte. Okay? And you examine, if they are not that, are they weak acid? Yes, weak electrolyte. Or they might be weak base. Weak acid, for example, you see that in one example already, HF. Pretty much any acid that's not in this 6. Again, just in this class, if you study organic, there's some other acid not there, but still strong acid.
For the soluble ionic compounds, are we going to be told that they're soluble, or is that something we have to know?
Yeah, you have to memorize. You already learned one part from chapter 2.
Okay.
You know what compound ionic, right?
Right.
So just review what we learned in chapter 2. You can identify what compound is ionic. 2 things you're looking for the ionic compound. One is metal, the other one is ammonium ion.
Right.
Okay.
But how do you know that they're soluble?
Yeah. So now remember that, you go to the second part, soluble or not. So this chapter, you have a table, try to memorize that table.
Okay.
Chemistry is a lot of memory. So memorize that table, and then you see if your compound satisfy both of these words, and then your compound is a strong electrolyte. Now finish this few examples here, so you have those weak acids. That is easy if you review or recall what we learned in chapter 2. You know the acid common reading in this chapter, in this class, is H first. 2 important about acid, H first, aqueous. Right? H2CO3 aqueous. That's another example of weak acid. Right? Any acid, not here. Okay? So HClO aqueous, this acid in like the swimming pool waters. It smells like the chlorine. That's the acid in swimming pool waters that will disinfect those waters. Weak base, there's a lot of weak base like those NH3 aqueous. That's one common example of weak base. So if your compound belongs to these 2 groups of compound, we call them weak electrolyte. And as you know, if you call them electrolyte, it means if you take those compounds, put them in water, they conduct electricity, so your light will light up, but not that bright because they will not 100% become ion. So a lot of them still exist as a molecule. Right? So you go cell by cell. So if you give a compound, you memorize these 2 smaller groupers. If they are one of this, you have the SE. Right? Otherwise, you have this. If they are not here, they are not there, then they are nothing. They are non-electrolyte. Right. So that's about this table. Now let's see. I think the next one is to emphasize practice how you write equation for the second process of produce a solution. Okay. So possibly you have two steps, but it's, if you have those two-step solutions. Okay? So one is let's say called A, dissolve, and B is either dissociate, ionize, or nothing happening. So this is the two steps you think about when you make a solution. Okay? You first dissolve, that means those something disappear in the water. Okay? Now what really happens when they disappear? Okay? They might become ion. We might just simply keep it intact. Okay? So if they become ion, you should be able to write our equation. So this is this process. Okay? So for the first equation, so I said pretty much do the reverse of what you did in Chapter 2. Okay? You see this compound is ionic. You have matter in it. Okay? And then later on you will study this. This is soluble. Okay? If it's soluble, you first want to add in here like aqueous. Okay? And then here will be Ca2+. Right? I add in aqueous because I see this problem is about dissolving water. Dissolving water means your state becomes aqueous. Right? So the other ionic compound obviously will have the opposite ion. You will have the positive ion, negative ion. Right? So you already identify the positive ion is the Ca, and Ca is the 2+. The reason is this guy is from group 2A. Okay?
2 chlorine.
Very good, Mike. So you will see that two Cl, 1 negative, and aqueous. So let me draw this line, and there are two compounds there. Right. So this is our first example. Our second example is our strong what? What is this HNO3? Very good. So that you put this aqueous, make sure that it complete. Now because it's a strong acid, so therefore I write only one arrow, which means it will be 100%. It will produce H+. That's the definition of H+. Well, this will be the characteristic of acid. What do we say acid in this chapter, right? There are some other definition of acid, so let's start from the first definition. And aqueous plus water ion. What with the other ion? Yeah, so this again, this NO3, 1 negative, is aqueous to this ion, and we have a name, polyatomic anion. Yeah, so keep it like a review, like there's a few very important polyatomic those anion or cation. So when you see them, so for most of the process, unless you have those redox reactions, you oxidize them or reduce them, so usually they will keep intact, and that part keep intact, but the whole molecule is still separated. Right? So by example, those subscript in the initial compound, you only have one H, so therefore you have one H+. Right? How many NO3 we have there? Together, only one NO3, so therefore we have only one NO3, 1 negative here. Right? So now let's move on to this last one. The last one is also ionic, even though in the last one there's no matter. Right? But remember, when you're looking for the ionic compound, you're looking for two things. Matter is the first one you want to look because matter is common. There's a lot of matter. Even though you don't have matter, you still want to looking for if you have that ammonia, NH4, right? Ionic compound is this. Right? So dissolve in water, which means become aqueous state. So this, I adding this aqueous, that means our step A is dissolved. Okay? Now think about this step B. Okay? Step B, will this keep intact, or will this become ion? What will happen for this compound? Ionic compound, soluble. If ionic compound is soluble, then what will happen to the compound? They dissociate. Okay? Very good. They dissociate into ions. Into what ion in this example? NH4. Very good. So we have that NH4, and this we call a cation because it has a plus charge, right? This kind of, from memory, you should memorize NH4 if ion will be +1. Okay? +1. What will be the state? Will be aqueous. How many? Yeah, very good. So now so make sure you practice on those, those numbers and the state. Okay? So remember this is called the state, okay? And also the formula, and also the charge. How many atoms are there? What are the charge? Right? So then plus, for the ionic compound, you always have the counter ion. You have the cation, then you should be able to identify the anion. So what is our anion in this last example? Right, very good. You have a CO3 and 2 negative, and we call that carbonate. And again, this is also anion. How many CO3 2 negative you will produce? There's only one. See the initial formula here? Only one CO3 together. So that's, and what is the state? If you finish, the state is what? Also aqueous. Right? So this process is very important because usually, you will get confused not because it's difficult, it's because it's tedious. There's so many details you have to memorize. So right now you know how to rewrite those equations into ions, okay? And it's very useful later on in those other sections. All right. So as I said, like what Don was asking, right? About rule, whether you see some compound is soluble or insoluble, and you should use that table. There's a table. I tried to make like a copy of it today, but I did not print out. And so for some compound, as I said, you don't have really a sharp cutting line. So any compound is liver soluble in water. Okay? So when we say those soluble or insoluble, what means more or less. And how we know those compounds soluble or insoluble? You can calculate in chapter, like chapter 17, like when you study chemistry 102. But at the beginning, those rules you get like about 300 years ago. So those simply from the experiment, from like those summary, okay? The so-called empirical method. So then this table, there are 2 tables about solubilities. So you try to like either try to memorize those tables, or you can print out like whatever way you feel like best, or make you memorize. Okay? So the solubility has about 2 tables. One table is called like the first table. Okay? You can see this has this 2 key words. Okay? So first table is about in general those ions here are given on the left side. So that means most of the time when you see them in the compound, your conclusion or leading to they are soluble. Because most of the compound have them innate is soluble. Right? You can see the word in general, right? What it means not always true. Right? So therefore you have those you probably will have those exceptions. And for the first few ions and no exceptions, I mean they were whenever you see this few ion and this few, you know there's no exceptions. I think that's straightforward. What I want to emphasize is what do we mean by the exception? And usually that's confusing. So in general, for example, whenever you see that Cl in your compound, you see that many times. So I have NaCl, I have KaCl2, calcium chloride. Even I can have iron-3 chloride. Anything has a Cl in it. That's why we give that name. So in general, they are soluble. But be careful with those exceptions. That means if I have the Cl and I have the Ag in it, if I write AgCl, then you know this become S, and then this few become aqueous, and aqueous, and aqueous. Aqueous, which means soluble. Now this S, another confusion, that's coincidentally S have the same letter as that S, so the process as S means soluble. Now this S is actually come from different, means solid. Understand? Right. So that is how we understand this table. So if you see these few ions together with those exceptions, that means it becomes insoluble. Let me give another example if you can identify this. Is Na2SO4 soluble or insoluble? It's soluble. How do we know that it's soluble? You can either use Na. So anything has Na in it, no exception. Anything has Na in it, no exception. So even though in that example Na is together with SO4, when I say anything has Na, which means Na together with anything. You can see in this example Na is together with SO4. No matter Na with what, it's soluble. Or you can use SO4. What SO4 will tell you? SO4 will tell you in this table, they tell you in general it's soluble. Which means anything has SO4 in it, your first impression is soluble, then you examine those few exceptions. If you have SO4, you also have those guys in it, and that becomes insoluble. If you don't have those guys in it, even though you have SO4, it's soluble. Right? So therefore this, either way, you can use Na, you know that is soluble, or you can use SO4 that is soluble. Right, so what about this guy? What about if I write PbBr2? Okay, no, that's insoluble, right? Because in general, what it means, if you don't have this three guy pair up with Br, then you know anything else, not this three with Br is soluble, but if you have Br with these three guys, it becomes insoluble. Alright, I think that's good, that's good. So that's, and then we do the second table. Second table is opposite. Okay? So these few ions, they are usually in general, if you see these few ions in the formula, then your first impression is those guys is insoluble. But then you see if they are together with this few, then they become soluble. So remember you need to have the mind switch. So in general, they are soluble, those exceptions make them insoluble. And then this table, in general, they are insoluble, so the exceptions make them soluble. Right? Right? So if you see this OH innate, okay, for example, if I have a FeOH2, the so-called RN2 hydroxide, right? Well, we name it compound. OH called hydroxide, Fe is an RN, but Fe with RN can be 3+ or 2+, so therefore, it's not that a group of 14, and you have to use the metal name with Roman numeral, right? So that's kind of quick review. So maybe show you quick review because I think we have the first exam next week, right? Or maybe the first exam next week. Or maybe not after next week. Right. So now actually, if you have this Fe OH2, so RN2 hydroxide, and you want to identify is this compound soluble or insoluble? Right, let's see this table. So in general, this table is in general insoluble, which means whenever you see Fe, like hydroxide in your formula, is insoluble. Okay? Then you see those exceptions. Okay? If you see those exceptions, they become soluble. Okay? So then you write them side by side. Okay? So if I have the other guy like this. So if I have Fe like the OH2, and I have LiOH, which one is soluble, which one is insoluble? Li is soluble because you have this exception here. Yeah. What about the first one? What about that FeOH2? Is that soluble or insoluble? So in general, when you see the hydroxide in it is insoluble, then you see this few exceptions. If there are few exceptions, but even though like this few, like we call them soluble, they are slightly soluble. So slightly soluble, we also consider them as soluble. Right? Right? Pretty good. I think you have a good understanding, and if you have a good like this, have a good like sound like this, so then you should just you don't forget. Right? I'll do a few practices. I think those are kind of easy questions, especially like on the exam, because you really you don't need like too much of just need some memories. Predicting whether each compound is soluble or insoluble. The first one is PbCl2. PbCl2. And in the table we don't have like you don't have like one table. We have remember two tables. So that the first table for those are most of them is soluble. The second table for most of them on the left side is insoluble. Right? So for this, I think for the first problem looking for that negative ion, the Cl1 negative here. Right? So in general, when you have a Cl in it, it's soluble. Right? The exception in general is soluble. Right? Exception, well, the exception for the Cl and the Cl and Br and I. So these three guys together. So in general they are soluble. What are the exceptions for these three guys? Yeah, so you have silver 1+, and you have the lead 2+, and then you have what? The mercury. So this the three exceptions, right? So what do you think of this one? The soluble or insoluble? Insoluble. Insoluble, you can use a word, you can say this is insoluble. Or you can use a state. If you use state, what letter shall we use? Shall we use S? Alright, very good. So what about the second example? So this one, the second example name, I just want to remind you, so that's called copper Then you not simply call the copper chloride, you have to call copper carbonaceous. Okay, very good. So you said it's 2, right? So then you have to use Roman numeral 2. Copper 2 chloride, is that soluble or insoluble? Yeah, so soluble, then therefore you're going to use what? Aqueous. Or you can just tell me in words this is soluble. So 2 ways to have the information about something soluble or insoluble. Right, so let's move on to this guy. So what word am I going to say this one? Soluble or insoluble? Yeah. Soluble. I think one way to know this very quick because you can use this ion, like this ion, right? Nitrate ion. Right? In general, is soluble. Are there any exceptions of this ion? So, no exception. A very, very particular ion. And we use those ion, we use like nitrogen ion like this in the lab a lot. So you can produce, you can pair this up with any protein ion, and it's soluble. Right, soluble, so therefore this will become what? Aqueous. Okay, now what about this BaSO4? Very good, so S and insoluble. I think that's very like straightforward memories. Now let me erase that and so we will see the. I think that's also practice. Right? Also practice. So what will be the first one? The nickel 2 sulfide. That's insoluble. You go by the sulfur. S2 negative. There's only a few exceptions like those Li and A ammonia. And then a few those group 2 like Ca2 plus and Sr2 plus and Pe2 plus. This Ni not in the exception. Okay? So the first one is insoluble, so therefore the stated S. What about this one? Also insoluble, so we have that. Also have one rule for the phosphate. So that is insoluble. What about this guy? Soluble. Anything has Li soluble. What about this one? Anything has Li, anything has ammonia, and H4 is soluble. Right? So that's makes sense. Right? So let's, for the first CRE about solubility, I will give you the table. I just want to make sure we understand these two tables. So first table is in general they are soluble, so the exception is insoluble. The second table for those ions in general they are insoluble. If you see those few ions with those exceptions, they become soluble. Right? What do you think about this one? The first one, this one, but we saw the following compound. We have like 5 of those following for the compound, right? What do you think? Which one is insoluble in water? D? Everyone agree with D? Very good. So then you can say that's the one CRE. You have a different way, to. I mean, I can have a different way to ask you about the solubilities, right? So if we have those soluble ionic compound, or those soluble and those strong acid or weak acid with a base, and they become those sort of electrolyte. So we saw the following. We saw the following will conduct electricity.
Is it A?
Is only A. Okay. What about B?
No.
B is no. What about C? So remember those, only these first two group of compounds can conduct electricity. Only these two group of compounds conduct electricity. The first group will conduct electricity very, very good, the light will very bright. The second one conduct electricity, but the light not very bright. Right? Then you can see only the first one that silver nitrate, the silver nitrate belong to this smaller group, right? It's ionic, it's ionic. Because you have silver in it, you have Ag is metal. Not only ionic is not enough. You have to see whether your ionic is soluble or not. Is your ionic like the AgNO3 soluble? Is the AgNO3 soluble? Huh? Is this soluble? You depend on the NO3, that's nitrate, right? Anything has nitrate soluble. Okay, why not there's sucrose and ethanol? Why not sucrose and ethanol? Why they cannot conduct electricity? Why they are non-electrolyte? Very good. So they are not ionic, therefore they are not this group. Okay? Then you have still can use them. Are they weak acid or weak base? Okay? So for the weak base, pretty much I give you only one example. You can memorize that, and there's some other weak base. Then weak acid. Weak acid, there's a lot of weak acids. Then how do you know those weak acids? Just use the elimination rule. So this 6 acid I give you, which means a strong acid. Now this sucrose and ethanol, so both of them are not acids. Typically the acid will have the H written first and has the aqueous. Right, so I think that is right. So the first one. Alright, so now this question is about this first type. Right? So which of the following is a strong electrolyte? So here in this CRE, I only give you one other possible choice, which is all soluble ionic compound. I did not give you the strong acid because we did not study the strong acid yet. But here I jump like one step.
Is it D?
D. Okay? So that means 2 of the above is a strong electrolyte. So which 2 are the strong electrolyte? Which 2 are strong? A and B. Okay? Very good. A and B. Okay? Why A and B are the strong? Why A and B are strong electrolytes? Both A and B is what type of compound? Ionic. All the way to the ionic. Because both has metal in it, right? So you see this table, keep like review this table. It's very like simple. To be a strong electrolyte, either this one or this one. They cannot be both. Okay? So any of this first one is a strong electrolyte. Any of this one will be strong electrolyte. Yeah. So the A and B both are ionic, and then you use the solubility table, and then you know both of them is soluble, right? So anything has BRN8 soluble, you can sell the Ag, mercury, and Pb, right? And then anything has NO3 soluble. So therefore, both of them, right? Both of them satisfy these 2 words. Soluble, ionic. So I give it out again. You have to examine both words. If you have only one word, that's okay, it's not okay. So many different ways to examine your memory about that 2 tables. And also part of this table here. Right? Which of the following compound is insoluble in water? Yeah. So C is actually very common, like those chalk, or like those blackboard chalk, and also like the shell of crabs, shrimp, and yeah.
What is that word?
That the solid. This solid. Is I don't know exactly, but I think it's something like chromate. those are some chromate. The chromate, right? Chromate is Cr04 2 negative. Right. Any other questions? Right. So the substance dissolved in water that cannot conduct electricity is called what? Yeah, it's very straightforward. So when you see something that conducts electricity, maybe conduct electricity very good, maybe like very little, but as long as this conducts electricity, you will call them electrolyte. If the light are very bright, you call them strong, and light are very weak, you can call them very weak. But that is from like your observation, just by observing the light. If you like observing those compound formula, compound type, so you have this picture here. Right? So this is very good, so very straightforward. Right? So now, if you see like when you mix some like those solutions together, like what you said in that picture, I saw from them like some chromate. So you make some clear solutions, and after you mix, you see those solid precipitations, and those kind of chemical reactions, and we have a special name for them. Okay? We call them precipitation reactions. I think this is one of this topic in this chapter. Okay? So we learned different type of chemical reactions. So this is one type of chemical reactions. Learning type of chemical reaction is a good way of learning chemistry. Okay? Because different type of chemical reaction will produce different products. Okay? And they will have a good pattern. Be able to predict the product is very important in chemistry. So in the precipitation reaction, okay, one of the products, it will be the solid. And the solid it produces has a name called the precipitate. Let's see in this example. In this example, we know this solid is lead 2 like iodide. And it has a formula PbI2, and that has a state S, which means solid. You can see what we said on the last slide, true. So we take two clear solution, two clear aqueous solution. This is clear, clear means which means no solid. So you have no solid solution and no solid solution. The solid coming you see here is not because this solution, it's because these two solutions mix. Right? And this type of chemical reaction called precipitation reactions. Okay? And so you can learn those different types. So you can see what we said is true. So one of those products of this precipitation reaction is solid. Now let's study how to predicting which of those compounds after you mix is our precipitate. So therefore you can tell whether you have a precipitation reaction or not. So sometimes you don't have the precipitation reactions. For example, you take that Ki, potassium iodide aqueous solution mixed with sodium chloride aqueous solution, and you switch those partners, and you get KCl aqueous and NaI aqueous. Then you use the solubility rule, you find out KCl is soluble, and any I is also soluble. So therefore, after you switch the partner, after you put them together like this in this picture, there is no precipitations. So then you can see precisely, you probably want to see here, no no precipitation reaction. For this example, I know you can also see there are no chemical reactions. What I want to say is that in general, if you mix two clear solutions, even though you don't see the solid precipitate, there might be also chemical reactions. But that is not like, we in this chapter will not see those so complicated. So therefore, we can make it, our study paper simpler. So if you start with two clear solutions and you don't see any precipitate, any solid, you can simply see there is no chemical reaction. But as I said, in general, that's not true. If you mix two clear, you still have clear, you still have chemical reaction. I mean, you still possible can have chemical reaction. Right? So let's start like something simple. So if we start with two clear solutions, and if we'll see like this is what this two we see now with examples, right? Right. So as I said, we want to study how to predict what is our precipitate, or in general, how to write the formula for the precipitate if there is a precipitate. In the same time, if we study this technique, and we also be able to tell whether we have the precipitation reaction or not. So what you do, you just try to identify your reactants. So you just try to write up what is your formula for your reactant and what is your formula for your products. Okay? So as we know before, your reactants, in general, you write the reactant first and products on the right side. But after you study chemistry level 2, everything becomes scrambled because the right side can become reactant and you can do the reverse reaction. So right now you see you're starting from the left side of reactant. Right? So usually the word problem will tell you you take what mixed with what, that means that will be our reactant. And now you have to review what we learned from chapter 3 or chapter 2. You have the name, you should be able to get the formula. Potassium carbonate, what is the symbol for potassium? It's a K. Okay? And what is the carbonate? Yeah. So it's very important to recognize, those or to memorize those formulas. So what is the charge for potassium? K is a plus or negative? Plus 1. So very good. Plus 1 because group 1A. Right? So this is our 2 ion. This is our 2 ion in for the first reactant. Okay? You can continue on with what we learned in chapter 2 by switching the charge as a subscript for the other one and get the formula. Okay? But here, let's see, probably can, for right now, for this, you can do that later, you can do it now. Let's see, we'll do that later. Okay? So let's identify the ion in the other reactants. What are the ion in the other reactants? Nickel, okay? Ni, okay? And Cl is chloride. Chloride is chloride, that means Cl1 negative. Right? Cl1 negative. Right. So then, what will be the charge for this Ni? What is the charge for Ni? Very good. How do you use plus 2? Yeah. So this Roman numeral will tell you the charge number. So there's 2, and you have Ni 2 plus. Right. So what I write here, did not go forward to get the complete formula because I want to emphasize from the ion in the 2 reactants, and you write them like in this format. You do the so-called a technique called double cross, and you'll be able to predicting the possible products. Okay? So let me switch the pen, and if I do the double cross, which means I want to cross like this. Okay? And I want to predicting the possible product. Okay? Why I say possible? Because you only have a product if you have a chemical reaction. Okay? Whether you have a chemical reaction or not depends on the driving force. For this type, and so far right now we recognize one driving force is the produce solid. Okay? So as we learn more, we'll see there are more driving force. Even though you don't have a solid, as I mentioned at the beginning, you still can have possible reactions. You might produce complex ion, you might produce water, you might produce gas, you might change those the electrons, which means the electron states in the last section. Okay? So you have different type of chemical reaction. For right now, we'll say if we mix two those clear solution and then two clear solution, both of them is ionic solution, we just examine whether we have a solid or not, we have a precipitate or not. That makes sense? So let's learn like little by little, right? So let's do the double crossing now. When we do double crossing, so that means I draw this line. This means I'm going to pair this K plus with Cl1 negative. Okay? So therefore I will write this together, K plus here, Cl1 negative here. Okay? So this is our one possible product. Then I'm going to say the plus, which means plus another possible product. What will be other possible products? If I do these two, I follow this line, and you should be able to pick out the other two, follow the other line. What are the other two possible ions? Will be our Ni, right? 2 plus, and then CO3 what? Very good. Yeah, so this is sort of double crossing. Okay? So we learn like little by little. Right? So in this, what we see this technique, we do double crossing. Now we are going to review what we learned before. If you have these two ions side by side, and you are able to get the formula by do the other double crossing. You take this -1, not the negative sign, put it here, put this plus there, so you get. So let me draw the chart. I seem to have this KCl. Right? Then let's also finish the other part. The other part, let me write it here. So I have Ni2 plus and CO3, 2 negative. So if we use what we learned in chapter 3, we will take this 2 negative, not the negative, just take the 2 and use for what? So let me write here. Ni2 plus and CO3, 2 negative, right? Remember what we did? I will take this 2 and use for Ni. I will take this 2 and use for this CO3, right? Now CO3 is a polyatomic, so make that notation clear, and you see it become Ni2, then parentheses CO3, and then 2 like that. So that is the immediate result after you do the switching, the charge becomes subscripted. But remember, you have to see if you can simplify. Shall we keep this as our final result? Or can we simplify? Simplify. So these two come out, right? So now our final result for the other possible product is this guy. Okay? Now let's finish our last step. Okay? So if we in this section, if we have a solid, then we already have the product. Otherwise, we see we have no chemical reactions. Even though in some other section you will see you might produce other, like water or complex ion. Right, so how do you know the states? What do you use to know the states for the KCl or for the NiCO3? So I run out of the, so what do you use? Tell me, is the KCl soluble or insoluble?
Soluble?
KCl is soluble? Yes, I think that's right? Why is KCl soluble?
All CLs are soluble, except silver mercury alone.
Yeah, so I think you're right. So anything has K in it, right? Everything has K in it is soluble, so therefore this will be aqueous. NiCO3 is soluble now. How do you know it's not?
It's not soluble.
Yeah.
Just because it's on the list and it's not, and it isn't really accepted.
Very good. Yeah. So that's S is solid. Alright, so if I have this and you want to write out this, I still want to keep this. And so you want to finish this complete equations, okay? And this equation, I will give you the name later on. So we have that K, and usually have that K plus and CO3 to negative. Now we will finish our, we have a chemical reaction. Okay? Now let's finish this guy. What is the formula for this guy? What is the formula for this KCO3? Alright, so I will erase this and then I will put 2 here. Everybody agree? And this will have the state aqueous. Alright, so the other one will start with Ni 2 plus Cl1 negative. So if you do a switching and simplify, the formula for this become what? NiCl2, right? And this guy is also aqueous, which is insoluble. You know that you use the solubility table. Right, so then now let's finish our writing the chemical equation, then we'll see how we balance. What are the 2 products from this picture here? So you have one is the KCl that become aqueous, the other one I will simplify. So we have NiCO3 that becomes solid, and then it precipitates insoluble. And this is the one equation in this chapter we talk about. Well, this equation has a special name. So this is one type of equation in this chapter you study. And this equation has a name called the molecular equation. And the reason for this molecular equation name is because in all those compounds we have here, the reactant compound, the product compound, they all use this as those neutral formula. Which means this is the formula you will see in the bottle, for those compounds in the lab. Okay? So then we will have some other type of chemical reaction. It will depend on what you want to understand. If you prepare those reactants, you just use those names from the label on the bottle. And then next type you will see, you put them in water. Water, do they really exist? And then you will have a different way, right? Right. So now we get the name. We know this first type is a molecular equation, and you balance this equation. I think you should be able to balance the equation by what we starting in chapter 3, right? How you balance this equation?
Just put 2 in front of the KCl.
So you just see this key. There are 2 key here, right? And there's only 1 key here. So if you put a 2 here, that will give you 2K and also 2Cl, and that's it. So you have this equation like this. Right, any questions? Right, now you do a practice. If I give you this word chemical reaction, let's see if you can identify what is your reactant and what is your possible products, if there's a product. In this particular example, you want to identify the solid product. You don't have to worry about the number. I mean, the coefficient like this 2. If I have 2, and in all those answers you don't have any numbers. Just identify the type. Is B? Right. So I think that's do a practice, and maybe that's right. Okay. Let me see your formula for the 2 reactants. What is the silver nitrate? What is the formula for silver nitrate? And what I did, write out the positive ion, the negative ion on the top for one reactant, right? Then write out the positive ion, negative ion for the other reactant at the bottom. Then do the double cross. Silver is Ag, right? Nitrate is NO3, one negative. So write what I did, remember in the example, write Ag plus. Did you like take the notes what I did in the example?
Wait, is it D or is it B?
The answer?
Yeah.
Do the practice yet. I don't tell you, because otherwise you tell you practice it. So write that formula for the first reactant. I mean, you have to only write that 2 ion. And what is the ion for Ag? What is symbol for Ag? Ag1 plus, right? What is the formula for nitrate? NO3 negative. Right? So what you want to write is something like this. Right? So you write Ag plus and NO3 negative. So these are the 2 ions for your first reactant. And now what are the 2 ions for the second reactant? Calcium, calcium and Ca. And the Ca is for what the charge for Ca? 2 plus. Right, so you write them side by side, and first level, second level. Okay. What is the chloride? Very good. So Cl, 1 negative. What we did for the example is doing what? Crossing. So when we draw this line, that means you try to pair up these 2 guys. Right, so therefore you will have this Ag plus and then Cl1 negative side by side. Then you do what? Cross the other 2, right? Cross the other 2, you get Ca2 plus and NO3 1 negative. Alright. Right. So if you have Ag plus Cl1 negative, you do the what we learned in chapter 3, and the final formula is AgCl. Right? And that you have the 2 plus and 1 negative. So what will be your final formula for that calcium nitrate? Yeah, so we'll have a Ca, then parentheses, NO3, 2, right? So then you identify what are the states, what is the state, what is the solubility for the AgCl. Here and here, what are the solubilities? Is AgCl soluble or insoluble? So that's S, and then this is what?
Aqueous.
anything has M3, right? So I think that therefore the answer is B, is right. Alright, so let's keep going. Identify the solid product formed from the balance equation of potassium nitrate and barium chloride. Now, this will be our number 3. Right? We have example of this CRE. So you can repeat what we did in for the last 2 problems. Right? Identify the 4 ions for the 2 reactants. Write them side by side, up and down. Okay, what do we have? Let me see your the 4 ions, the 2 pair of ions. Yes, let me see the 2 pair of ions. You get the 2 pair of ions. And what do we have for this number? Is potassium nitrate. What is the ion in potassium nitrate? Potassium nitrate. Good, good. Another one is barium what? Barium chloride. Okay. And then you cross out. Then what are the new possible combinations? That one guy, that one guy. Yeah. So what is the state of this? Is this soluble? What are the state? Very good. So you get that 4 ions, and then let's see you do the crossing and get the possible products. Use the solubility table. Identify they are solid or aqueous. Where is your 4 ions? Okay, that technique, very good, that technique. Okay, now be careful, the piece here. What do you mean by S? S is solid, S means solid, not solid. Okay, so what's the 4 ion there? That's the 4 ions. Yeah, yeah. Let's see, do you get it right? Okay, what do we get? E? Do you, yeah, so you get that technique, K and S, switch. Anything has to be soluble, anything can be soluble, right?
That sounds like a liquid. Is that what it's in?
Calcium always put on eggs, so it's gonna be solid. Yes.
Yeah, that's a good observation because you have the K put in a way and become insoluble. Also like the sodium, right? Right. I think the answer is E, right?
Yeah.
Right. So make sure you practice these few steps. Right. So that's blue solid. Right. So I think that's going to be fun. That's going to be fun. So you pretty much you're going to combine the last few chapters, all those what we learned. Start with what he just did for the last CRE. Okay? Identify the 4 ions and do the crossing. I think I already tell you like a part of the problem, but you still already aside from that. Then you are write an equation like what I did for the other problems. And balance it. And then use the first few sections of chapter 4. Right. So let's start from what we just did for the last CRE. equation first. So make sure you get the balance equation. Yeah, I think I tell you my products, but if you don't know like the other products, repeating what we did for the last CRE, and you first write out that 4 ion, do the double crossing. What is the 4 ion you have? Okay, kind of good. So this is 1 and 1, so you don't have that two. Make sure balance equation. If you put 2 there, there you go. So now you're starting from this, so this is solid, right? Alright, so get the balance equation first. Let me see get the equation first. Okay? And then we'll study how to use the balance equation where we use the coefficient to get more ratios. Did you get the equation balance? Okay, you get the product line, so that's PBI2 and KM3, and you don't have a reactant. Okay, write out the formula for the reactant. Pretty good. Once you get the subscripts, in your chemical equations, if you have the subscript for the ionic compound, you can drop the charge. Because the charge and the subscript is kind of duplicate. You get the subscript from the charge. Right. Okay, try to work on the equations and get the equation first.
Is it A?
Probably. Let me see your. Do you get the balance equation yet? Okay, PI that's good, and P that is good. See, you have this, you want to cross these two out, right? So what is, to tell you, like, I think those already tell you like that, 2 of those reactant formulas, right? One is the KI, the other one is the PB, M3. Why do we have, we don't have that, right? And M3, so M3 is 1 negative, right? So that's called nitrate. So that comes backwards. So you just, whenever you see like the says -3, that means it's -1 charge. You have -1 here. So when you identify that 4 ion, make sure you identify what are the atoms there, what are their charge. So this is -1, that's a +2. Okay. Now you go into the cars, and you just write the PB2 plus. On like from PB2 plus, and then I1 negative. So I1 negative here, right? Then you switch 1 onto PB, switch 2 onto I, and then this one right. This is right? Now you do the other one. What do you do for the other one? Yeah, K1 6. Okay, good. So you get both of them right. So now, this is 2 possible products. And I think the equation tell you, like, kind of tell you, like, which one is solid, which one is precipitate. Which one is precipitate? I think this one precipitate. This is solid, so just you put this there. And the other one you overlay. And yeah, anything has a key in its equals. And now let's finish the other problem. So you write this on the right side, this is the product. And now so you write the state. What is your two right things? You draw arrow here, right? What will the formula for two right things? That's 2, 2, right? So the one formula for the right thing is what? No, for the right thing. Yeah, this one right thing, and the other one the other right thing. The same as what you write there, right? So right down here.
With another diamond.
Now we don't have right, just write formula. Pi equals. The other one is PV -3 and PV equals, those are equals, right? Okay. Now try to balance that, that's good. So we have the two everything and two products. Anyone need help to write the equation first? Okay. So let me put the equation here. Right, so the equation is like this. So you have that Pi equals, and then you have that PV angle 3, 2 equals. I omitted those swapping, switching, those steps. I think most of you already know how to do that, and you will get what? Right, so these are the two products after you use double crossing and so on, and after you also use what you learn in Chapter 3. Now let's balance the equation. How can you balance the equation? How many I right now we have on that side? And how many I we have here? So therefore you put 2 here, right? If you put 2 here, then how many k you have on this side? And then you do like something like this. That's okay because you have 2k, you also have 2 angle 3, so therefore everything is balanced. Right? So then, once you have that, you are going to use what we just learned like at the beginning of today's class. Use the volume and the molarity to get the mole for the two right things. And now let's do that. Let's get the mole. Get the mole for the right thing, the Ki, from this information. And get the mole for this PBM3 from that two information. That's what you just learned today at the beginning. How can you get a mole? If I tell you the volume, I tell you the molarity. So remember what we did today at the beginning, like the first few slides, and you just do something like this. So you can change the volume into like liters. So this becomes how many liters? 25.0. I will omit the step. You will check by yourself. This becomes this amount of liters. And also omitting like what I told you at the beginning. If you have this capital M, you can write this information into a fraction, right? Right. So this becomes like 1L over, something over this 1L 0.150 more Ki. Right. So this will give you how much Ki. Right. Similar for this one we'll do something like 0.0150 L and 1 L over 0.175 more of PB angle 3, 2. Alright. So you summarize these two information, take a notes, write like if you don't like write what I write, then later on you can just later on what to read. Alright. So now you multiply those numbers, let's see how many more of Ki do we have? And how many more of Ki? From the equation too, but from this number. From this number, when you take a 0.025, 0.00375, right? So that is how much more of this Ki do you have from this equation, right? So how many more of this PB angle 3 do we have now? From this second equation. 2625. Right? Now you know the next step. Now let me rewrite this one. 0.002625 more of this. Okay, now what the question about is to find out how much something can produce, right? Its attitude is about limiting reactants and theoretical yield. So that's about those kind of questions. Right? You have two reactants, you have two moles, and how can you find out how much you can produce? The procedure is like what we studied in the first section of this chapter 4, is starting from the mole. If you have the mole, then we'll see the few steps, right? And use the mole ratio convert into this product. Right? So what are mole ratio between this Ki and this PBI2? And so we have 1 mole of PBI2 and then 2 mole of right. So that will give you how much more of PBI2. So then you will do the same conversion by using this. What is the mole ratio between this PB angle 3, 2 and this one? It's 1 to 1. So 1 PBI2 and 1 PB angle 3, 2. Right? So do this calculation and you figure out. So this obviously is still the same number. How much we have there? 0.0016 1675 1875, right?
Mm-hmm.
Okay, what do we do next? So you have this same products, but you have like what? You have two different numbers. Because one number is based on this number is from this reactant, right? And the other number is based on what? That reactant. Right? What do we do now? Compare which one is later or which one is less, which one is more. Right? The last one is called what? Alright, so this is our what? Theoretical yield in more, okay? Because this theoretical yield in more comes from this, and what do you call this? So therefore, you are just do one more step, use some more of this, converting into those into what? What are the answers? What are the answers in, what are the choices? So how can you get a gram if you do the power? Theoretically, you can get this number more of the products. What do we use to convert into those numbers? Molar mass. Okay? So starting from this number, not this number. The answer is what? What's the answer if you start with this one? Is A. Alright. So I think this is
Can we get a few minutes to do this class table?
yeah. So everyone write the results on the blackboard for the last experiment. To save time, now each group write one place. Yeah, just work out. Yeah, for the food content, for the animal content of the food.
So,